It's my pleasure to introduce to you today Sara Ferraiuolo. She's a PhD student at the A Marseille University in France and also at La Sapienza, University of Rome. And today she will be talking to us about inferring astrophysics and cosmology with compact binaries and their stochastic background. So please, Sarah, feel free to start whenever you're ready.
Okay, yes, thank you for inviting me. Today I will discuss how we can use the gravitational waves to from compound binary coalescence and the stochastic gravitational wave background to infer a key aspect of astrophysics and cosmology. I'm working with my supervisor Simone, Stephanie, Eric, Kashfaz, which are ex-Marseille University and Simone in Sapienza University. So this is the outline of my presentation. I will discuss how gravitational wave can help to infer cosmological parameter, in particular the Hubble constant, and the motivation to doing so. And then I will introduce the methods that we use to analyze the data, the simulated data that we produced. We are using LBK at A+ sensitivity and the results for this simulation. And finally, we also tested the pipeline with reanalyzing the GWTC3, which is the last catalog that we produced with LBK collaboration. So, as we are all aware, the universe is expanding, but the measurement of the expansion has been a central focus for in cosmology. And a lot of people have attempted to measure the Hubble constant in the way, for example, we're using type 1a supernova or CMB, but getting increasingly better precision as they go. But something really interesting is appearing the better this measurement gets. As we can see from this figure, which represent all this measurement, we see that the method using early measurement, which are the one on the left, try to prefer a lower value of the Hubble constant, while the late measurement, which refer to local measurements, tend to favor higher value of the Hubble constant, and there is a growing tension with these two values, as we can see from the plot. Currently, it's not known if this tension is due to systematic that potentially affect the local measurement where astrophysics make everything a bit messy, or if there is some new physics behind the standard model which infer a local value which doesn't match the one measured locally. So it will be very nice to provide to another independent way of measuring the Hubble constants and potentially arbitrate between these two cases by agreeing, for example, with one set of measurement or the other. That is where the gravitational wave came into. Indeed, the strength of this method that is that they provide the distance to the source independently, making these events as the so-called standard sirens, analogous to how type 1a supernova are used as standard candles. One of the big advantages of using gravitational waves for cosmology is that they can potentially provide the measurement of the Hubble constant in a very wide range of distances, from nearby universe to very further away. And this comprehensive range can help understanding the universe expansion history. Yes, this is a brief introduction. Yes, you probably know the gravitational waves exist in multiple forms. The transient from compact binary mergers, CBC. I will call them in the next slides. They are the one that we already detected. Then there are the bursts, continuous waves, and stochastic gravitational wave background, which in LVK we never detect them. And stochastic gravitational waves is a superposition of many unresolved and weak signal, as we can see from the plot, but I will explain a bit more later, because they are a part of the source that I will be used in our analysis. Going back to standard sirens, we know that if we want to measure the Hubble constant, this is the redshift luminosity distance relationship that we can use. As we can see, the main ingredients that we need are the luminosity distance, which, as I said, is directly encoded in the amplitude of the gravitational wave signal, without any external calibration. So that's how the gravitational wave measurement of the Hubble constant would provide a completely independent, will be completely independent to the other measurements. And the other piece of information that we need is the redshift, which is slightly more complicated because the redshift is degenerate with the mass in the gravitational wave signal, so it must be found in other ways. The ways that we use with standard sirens are, there are a few methods. So we detect a gravitational wave from a CBC. We ask if there is electromagnetic counterpart. We use the bright siren method, which is so if you have an electromagnetic counterpart, you can obtain the host galaxy redshift. So it's pretty easy, as it was done with the gravitational 7017, and the host galaxy identified was NGC 4993. And so for that, we get the redshift measurement of this host galaxy. We can measure the Hubble constant. If we don't detect an electromagnetic counterpart, we have two methods. We have to infer the redshift in other ways. And so one potential thing is to use the relationship between the mass at source and mass at detector. Indeed, we know that the mass, we measure the mass at the detector, which is the mass at the source redshifted. And so if we assume some mass distribution, we can break this degeneracy and get the redshift. The other one is the dark siren method, which basically provide the galaxy catalog, provide the potential redshift of the source. So it requires identify all the galaxy within the localization volume of the gravitational waves event and treat them as all natural hosts, marginalize cover them at some point, the true host galaxy will give you the correct value of the Hubble constant, and the other will average out. We will use the spectral sirens method in this work. Just to be complete, I want to give you also what are the current results for LVK. So using the GWTC3 catalog, which is gravitational wave transient catalog 3, so the last one. And this is with GW70 with the posterior on the Hubble constant, which we see it's pretty informative, but we only have 1 point. And so we must rely on other methods. This is why we also use dark siren methods. This is the results using the GLADE Plus catalog. So this is a patchwork of many different galaxies, and these on the plot are the posteriors on the Hubble constant using, for example, the orange one is using the K-band, and the blue one is the dark siren method combined with the GW17017, which we see it's more informative. And I don't know if you see the dot gray curve is the spectral siren method. So it's the empty catalog. So we treat it as the catalog is empty. So we are mainly doing spectral sirens. So going back to my work, I used not only resolved sources, so compact binary coalescence, but also unresolved sources, which is the stochastic gravitational wave background, which can exist in many different forms. One is the astrophysical, in two categories, let's say, astrophysical background, which is the one produced, for example, from binary black hole mergers, neutron star mergers, which are very weak or very far from us, so that we cannot resolve. And the cosmological background, which is the one produced from, which has a cosmological origin, for example, from cosmic strings, and so on and so forth. For this work, we focus on the astrophysical background because it's the one that we expect to probably detect, and which is the most relevant, let's say, in the frequency range of the LIGO Virgo LVK detector, and they will be more dominant in the data of the interferometer. Usually, it is characterized by this dimensional energy density, which is where we see that is the we have the rho GW, which is the energy density in gravitational waves per logarithmic interval, and rho C is the clinical energy density required to close the universe. More specifically, we can write it like this for a CBC population, and we see there are three main ingredients, which are the RZ, which are the merger rate of gravitational waves per conmoving volume per moving time as a function of redshift. Okay, this is the merger rate. And there is the energy spectrum in gravitational waves radiated by a source, averaged by a source population. And this is where you plug your information of for astrophysical properties. As we said, the stochastic gravitational wave background is a superposition of events coming from all the universe. So there is also a cosmological term that enter and which is encoded in this term. The stochastic gravitational background scales as h0 at -3 because and this arises mainly from the merger rate the commoving volume density term, which is encoded in the merger rate. So following the Turbanger and Callister methodology, we combined the likelihood. So talking about the analysis method, we defined a joint likelihood by combining the individual BBH events, CBC detection, let's say, and the stochastic gravitational background to infer all the hyperparameter lambda consistently with these two sources. So then we proceed to simulate the data that we did using LVK, like Obligo at A+ design sensitivity. So first we simulated the stochastic gravitational wave background. We simulated the parameters CF and sigma F, which are the cross correlation parameter between different detectors. We assumed some mass model, some rain model, which are the power loss plus peak and Madao rate for the rate. And these are the gray dot are the simulated CF. The blue curves are the 1 sigma and 2 sigma lines, which are basically the sensitivity that we have for the stochastic gravitational wave background. And the red curves are the theoretical the expected omega GW energy density for the stochastic gravitational background, which we see it scales with the h naught. And so for lower value of the Hubble constant, we have a higher energy density, and vice versa. And so if we do not detect a gravitational wave background, we can exclude some ranges of the Hubble constant, some part of the Hubble constant values. Then we also simulated the gravitational waves, so the resolved sources using the same model. We also do the parameter estimation, and these are some posterior sample for the mass, detected mass, and the luminosity distance. And then when we simulated all that, we built our catalog. We actually did the analysis with two independent observing scenarios. The first one is the resolved sources. So we have 2 years of gravitational wave data only, the resolved sources. So we have 1,200 BBH. And the other scenario is we detect 1 year. We use the detector only for 1 year, only to detect gravitational waves from CBC, so the resolved sources, and we get 600 BBH. And then we use the other year to only detect the stochastic gravitational wave background. In this way, this is motivated by the fact that the stochastic background removing the resolved sources would decrease of 30%. So actually, in the joint likelihood that I defined before, I assumed the resolved sources and the stochastic gravitational background to be independent, but they're actually not really independent. There are some cross correlation between these two sets, and to avoid that, we did this 1 year collecting only resolved sources and 1 year only detecting stochastic gravitational wave background. So given that, we did our analysis with these two catalogs. And these are the results for the cosmological parameter. So the pink curve is using only individual, so the resolved gravitational, the 2 years of resolved gravitational waves, while the blue curves is using the catalog that combines stochastic gravitational wave background and resolved sources. We see that actually we don't the most of the precision is given by the resolved spectral science, because we don't get any improvements, let's say, with our methodology, but we are able to exclude some region of the low the parameter space, the low values of the Hubble constant and omega matter. So it helps to exclude this region of low values. And we are also, yes, that's it. For the rate parameter, we get some improvement in the zeta peak, which is the peak of the merger rate distribution, and gamma, which is the parameter that governs the low redshift rate of merger rates. And for the other parameter, actually the individual, let's say the standard analysis works better. For the mass model, we also don't have any improvements. And so the spectral siren analysis is still for performing better and giving all the dominating the results. These are also some posterior predictive checks to evaluate the improvement These checks involve reconstruct distribution derived from the posterior predictive check. So we see that when considering resolved sources alone, the reconstructor redshift distribution, which is the first row, we can see that the measurement at higher redshift, so for the Z measured and zeta peak, we have a better constraint on the merger rate. This is because of the information given by the stochastic gravitational-wave background, and since we measure better, we can exclude some parameters of Hubble constant omega m, and also because we measure better zeta peak and gamma. And also yes, for the mass model, we don't mass distribution. We don't get any hint for the. Of course, when we detect the stochastic background, we get a better constraint on the omega GW, the energy density of the stochastic gravitational background. We did also the analysis of GWTC3 just to check that everything was working, but we already expect to not get any improvements because in GWTC3 we didn't detect any stochastic background, while for the analysis we actually, as we see, the sensitivity curve is falling above the omega GW energy density, so we expect to detect it and to gain information. Yes, these are the posterior predictive checks, but as I said, they are more or less similar, the two analyses. And these are the conclusion. So with future detector, we can, the inclusion of the stochastic background can help to understand the astrophysical and cosmological parameterization. This is, of course, an explorative study, so we made a few simplistic assumptions. We can be revised with a follow-up study. For example, we assumed a likelihood which is independent, but can be built differently, and we also don't include any BNS and SBH background. And that's it. Thank you for your attention. You can, any question, I'm happy to answer.
Right. Thank you, Sarah.